Really?
I took it on Monday. I took it on Friday.
But he always likes to say, yeah,
Okay.
Better than his age.
not too.
Okay, so questions.
Oh, he used to tell us that.
What are your questions?
Can you go over the electrophile formation, please?
The electrophile formation.
Like what adds on to
Okay. What else? I'll just make a list and then Rhea.
When you're naming a benzene segment, you should, the parent name should be a toluene or a nitrogen.
Okay.
The Pharma Aromaticity absolute kind of confused with the
Versus non. Okay. What else? Okay, we can start from there. Let's deal with the naming first. So there are certain groups that when they are attached to a benzene ring cause the name of the molecule to no longer become benzene, the parent name. So for instance, this is benzene. When I add a methyl group to it, that becomes toluene. When I add a methoxy group, it's no longer benzene, it's anisole. Say that very carefully, but it's anisole. So the other ones would be two methyl groups as a xylene. You have your benzoic acid, etc. So if the group changes the name from benzene to something else, that group then automatically gets the number one position in the numbering scheme in the naming. Okay. And so you have a sheet that has a lot of those names. Those would be the ones that you would be responsible for. Okay. Nitro is not one of them, nor is bromo or chloro. So when you add a nitro group, you make a nitrobenzene, but benzene's still there. Or a chlorobenzene or a bromobenzene. It's the benzene hasn't changed. Therefore, that's treated as if it was any other group. Okay. So that's our rule for naming. If that group changes the name of the benzene, it automatically gets the number one position. Right.
That's similar to how you adopted common names where we should just memorize all of those.
Yeah, they're not even common names. They jumped right to formal IUPAC names. So toluene, anisole, benzoic acid, benzaldehyde. What else was on that sheet? Which ones? Aniline with the NH2, phenol with the OH. The benzyl alcohol, yes, that changed. And then there's benzoic acid, benzaldehyde. So anyone that changed from benzene, changes the name from benzene, you automatically, that group gets number one position, and the parent name changes to that name. Toluene, xylene, etc. Okay. Does that make sense? But the nitro is not one of them, chloro, etc. are not one of them. Okay. Let's do anti and non-aromatic. Did anybody give this molecule some thought? from the end of Monday? But he want to volunteer an answer?
Anti-aromatic?
Non-aromatic. I got 2 antis and 1 non. Anybody want to throw their answer in?
Non.
Non. 2 nons, 2 antis. Non. Yeah, you're
I count.
they're kind of piling on right now.
I count. Do
Do you want to change your answer?
Yeah, it's not.
Is it obvious that it's non? Because it's not obvious that it's non.
Well, that's okay. I'm asking for answers, and then we'll go back through and we'll see what it is. It is aromatic?
I mean, I would say they're not saying non.
Okay. Any other answers? So this one I put 2 atoms in the ring that have choices. Right? So both the nitrogen and the oxygen could be either sp3 or they could be sp2. Our only concern with it being aromatic is for it to be aromatic, both atoms have to choose sp2. Right? And what happens if they do that? So let's take the first scenario. Both of these atoms become sp2. If they do that, how many pi electrons do I have? 8. So I've got 2, 4. If this nitrogen becomes sp2, the lone pair goes into the p orbital. And if this oxygen becomes sp2, one of the lone pairs goes into the p orbital. So if that's the case, then both being sp2 would give me 8 pi electrons, which would make the system anti-aromatic. Which means the system would be very unstable. It would be the most unstable possibility. And that's if both atoms choose that. So what's the likelihood of both atoms choosing that? They're not going to, because this system's going to go to its most stable, and its most stable is not its most unstable. Okay? So then I could say, well, what if one of them chooses to be sp2? What happens? What is it? One more time?
If one's sp2, then are you saying the other one's sp3?
Yes.
Then it's automatically not aromatic, right?
I don't know. Does that sound good? Yeah. Okay. So if only one chooses to be sp2, you've got one sp3, so it can't be aromatic, so it's non-aromatic. And if they both choose to be sp3, then it's still non-aromatic. Now, the question of whether or not what the real structure would be, I have two choices to figure that out. Number one, I make this molecule, which I don't know how easy that would be. It'd be easier if I could just buy it. And then I would try and cool it down and make a single perfect crystal out of it, put an X-ray beam through it, I'd get its exact structure. That's a lot of work. Of course, I could look it up online or in the literature and see if somebody's done that before. My other option is I could put it on the computer and see what happens, and see which atom becomes planar if either of them become planar. It could be it's hard to say what would happen. Actually, no, that's not correct. Whether the nitrogens would be sp2 or sp3. So in this nitrogen case, if the hydrogen is in the same plane as these two guys, it's sp2. If the hydrogen is down, like in a somewhat equatorial position, or if it's like this, if that hydrogen's down here, then it's sp3 hybridized. The oxygen I'm going to have some problems with because I can't see electron pairs. So I don't know if the electron pair did this with one planar or if it went like this and went sp3. That I'm going to have a bit of a problem with. So either way, the best answer for this one is that it's non-aromatic because that's the most stable. So only one situation would give you anti-aromatic. It's not going to prefer that. The other two situations, well, the other three situations, nitrogen sp2 or oxygen sp2 or both, start all over. Nitrogen sp3, oxygen sp3, both sp3, non-aromatic. Now, why did I start with that? Oh, because the difference between anti-aromatic and non-aromatic. So first of all, we have to have an atom that can choose in the ring. And oxygens and nitrogens can choose. So can a C-. That's the other atom that can choose between sp3 and sp2. A carbocation cannot choose. A carbocation is forced to be planar. So it's forced to be sp2. But of the three atoms that can choose, oxygen, nitrogen, and a C-. Sarah, I cut you off. And sulfur. So now oxygen, nitrogen, sulfur, and a C-. I think that's all of them. So in the quiz, we have that anion. And so for that anion, what will it be? Will it be aromatic, non-aromatic, or anti-aromatic? And take a moment, and then we'll do cards. You can give your answer by card. We'll see what we get. Okay. So that was the one in the homework. So if you forget what you wrote, you can just pull your homework out and see what you wrote. But is it aromatic? Is it anti? Is it non? So we'll go in order of energy. So A is aromatic, B is going to be non, and C is going to be anti. And we'll leave off D, because D would be I don't know. And there's no points for I don't know. Okay? So what's this one? You got to get your finger. You have to move your, yeah, there you go. Your fingers can't be on the little square figure. Okay. What do I have? I've got 2 A's, 15 B's, and 8 C's. It's an interesting distribution. So let's go through the same logic that we did for the nitrogen oxygen. So C minus, can it choose?
Yes.
It can choose to be either sp2 or sp3. What's it gonna make its decision on? The overall stability of the molecule, right? So it will become sp2 hybridized if the molecule becomes aromatic. So whenever the molecule has a choice, it will choose to be sp2 and throw its pair of electrons into the pi system if the system becomes aromatic. Does that statement make sense to everybody? So in this case, how many pi electrons do I already have? 6. So I have 6 pi electrons. What happens if the carbon becomes sp2 and throws its pair of electrons into the system? I now have 8. And what's the significance of 8? It makes it anti-aromatic, which means if that carbon decides to be sp2, I've got 8 pi electrons and the ring is planar. That means the molecule becomes anti-aromatic. What's the problem with that? It's the most unstable. So the carbon's going to avoid that situation, become sp3, and the system then is just going to be non-aromatic. Because it can't become super stable with being aromatic. I mean, it could if it didn't have any, if that did not have any electrons to share. In other words, if that carbon was a plus charge, it'd be happy to be sp2 because then you'd have 6 overall 7 atoms. But that's the tropylium ion, right? This is the tropylium anion. Okay.
So when a molecule or a C minus chooses to be sp3, it no longer donates its pi electrons into the pi system?
Right. Because what happens is in the ring, you've got all of the p orbitals parallel to each other. I know that's not a very good ring, but I can't draw a 7-membered ring on its side. So then the carbon decides, okay, I'm going to do this. And so when it becomes sp3, it doesn't have a p orbital. It's got 2 sp3s. And so it doesn't line up the p orbital and doesn't create that continuous overlapping pi system. Rim?
So if it were to make it aromatic, then it would choose sp2 and make the whole molecule aromatic?
Yes.
Okay.
Yes. So where it would do that is this. I'll take that same molecule and now I'll give it a plus charge. Only in this case, the carbon doesn't have a choice. It's got to be sp2 because all carbocations are sp2. But let's give it a choice, right? Because there's lots of things where you don't have a choice, but people make it seem like you do. So that carbon, we'll give it its choice even though it doesn't have it, but it goes sp2 and what happens? Now there's 6 pi electrons, planar, aromatic. If that carbon had the choice to go sp3, it's not the most stable form.
So even if a specific molecule in the ring doesn't offer electrons into the system, if it allows the system to become continuous with its
Yes.
orbital, okay.
Yes. Then the idea is if this carbon over here decided to finally make it p, then I would have a continuous system. That's criteria 1. Criteria 2 is, does it fit the 4n plus 2 rule? So if it fits both those rules, it's aromatic.
So the one with the carbocation is anti, right?
No, this one is aromatic. That's the tropylium ion. That is aromatic. Because it's got 2, 4, 6. So all the atoms are in a plane, and it's got 6 total pi electrons. Because the carbocation has nothing to add, but its empty p orbital to make the system complete. That's how it works. Kitty?
So for N, like what are you supposed to input for N?
0, 1, 2, 3, 4. I'm counting my fingers. They literally are just integers starting at 0. So what happened was that when the whole idea of aromaticity came about, and the whole idea of benzene. So you've already seen that benzene doesn't react with CaMnO4. CaMnO4 is purple. If I take CaMnO4 and I put it with any other double bond, it will turn brown because it forms MnO2, which is manganese dioxide, but it will react with the double bond, right? Forming either a cis alcohol or it'll cleave it. But if I take a benzene ring and I throw potassium permanganate at it, it's purple. Potassium didn't touch the benzene ring. I heat it, it's still purple. I take bromine without FeBr3 now. I take bromine, I put it in the benzene ring with a benzene molecule. Nothing happens. So the first people that did that, whoever they were, they had to kind of say, well, I think benzene has double bonds, but why is it not reacting? And somebody must have said, oh, it's more stable, right? Because the stability of reactivity principle has been around forever. With people, it's been around forever, and it probably made a quick translation to chemistry so that we know that if molecules are stable, they're less reactive. So somebody said, oh, well, that molecule must be stable. And then the whole idea is, why is it stable? Which gets you to the idea of aromaticity. Right? So you still with me? I took a little bit of a diversion there. So potassium permanganate will not touch the triple bond. It's unreactive. Then I forgot the question. I'm losing it. What was the question, Kitty?
Like, what does N mean? Like, are you
Okay.
like aces, like carbon, like
No, I'm counting number of pi electrons. So let me finish. So now I can finish my story now that I know where I'm going, not just aimlessly. So then, in the studying of the aromatic molecules that were aromatic, that were super stable, what they found was they had characteristic numbers of pi electrons. They first of all knew that the molecules were all flat. So that was characteristic number 1. Then they found out that, well, some had 2 electrons. Some had 6 pi electrons. Some had 10 pi electrons. Some had 14 pi electrons. Some had 18 pi electrons. And so they could have just at that point said, if your molecule is flat and you have any one of those numbers that I just mentioned of pi electrons, you're aromatic. But what they found was that if I take the formula 4n plus 2 and I put in 0, and then I put in 1, then I put in 2, then I put in 3, that I generated that allowed number of electrons. So 4n plus 2 is the number of pi electrons. 1 double bond equals 2 pi electrons. And then you can generate that from the 4n plus 2. It has other consequences, just like 4n has other consequences. But for our purposes, that's what generates the number of allowed electrons to make the system aromatic. So if I said I have a molecule with like 32, it's got 32 pi electrons. then I have to figure out, is there an integer of 4n plus 2 that gives me 32? No. So it wouldn't be aromatic. On the other hand, if it had 38, it would be.
So let's say that nitrogen is double bonded to a carbon. Does that mean that the lone pairs are outside of the pi system?
Yes. So if a nitrogen is involved in a double bond, then that means that in order to form that double bond, it had one electron in the p orbital that overlapped with the one electron in the carbon's p orbital. And these pi electrons are in the sp2 hybrid orbital. So that will then make those electrons, that'll make that nitrogen basic. Okay. Does that kind of make sense? Okay. Electrophiles. So what we started with today was, well, I just went through this big spiel about how benzene won't react, right? Well, then it will react. But it needs to react with an electrophile, which makes sense because the benzene has double bonds. It's a nucleophile. But it's a really stable one. So that means I need like the strongest of electrophiles to react with benzene. Makes sense. If benzene is really super stable, it's going to take a really strong electrophile to react with it. So my electrophiles are all going to have positive charges. And the question is, so when I take my electrophile, generic E+, my generic E+ now is strong enough to add to any one of those double bonds. So the pair of electrons goes from the double bond to the electrophile. And I bond that electrophile to that carbon. That puts a plus charge there. And there's still an H off of here. Now that electrophile had enough electrophilicity to break up the aromatic system. But I now have resonance structures I can draw, right? So I could take this pair of electrons, move it here to form the double bonds there and there with the H and the E there, and then the plus charge there. And then I can take this pair of electrons and move it. I take this pair of electrons and move it there to then form a third positive charge there. And then I could draw the resonance hybrid of those three. Right. Now you didn't have to do this because this was on the PowerPoints, right? So nobody drew out all three resonance structures because they were there. But I could have asked you to do that because what am I doing? I mean, we've done this in the past, right? And not like 3 months ago. We just did this within the last 5 days. So if I'm adding the electrophile to one of the double bonds and then I'm forming these resonance structures, I kind of have a vague recollection of that being done in what kind of reactions? Dienes, allylic systems, so like 1 and 2 and 1 and 4 addition. Only this would be 1, 2, 1, 4 and 1, 6. Okay. So that can happen. If the electrophile is strong enough, it'll add into the benzene ring, and it'll do like a 1,2, 1,4, 1,6 addition. Well, but it did it? I didn't get 3 resins or 3 products, did I? Because adding a nucleophile to any one of those plus charges destroys the aromaticity of the molecule, which means it's not very stable. So what this molecule decides to do is, it says, you know what, if I lose that H plus, I can reform my aromatic ring, and what I've now done is I've substituted the electrophile for a hydrogen, which gives us electrophilic aromatic substitution. So the reason that happens is because now I can form the more stable product, reform my benzene ring. Everybody okay with that? So the question was dealing with electrophiles was what?
Formation.
The formation of the electrophile. So now that we've all agreed, or haven't posed any objection, that I can add any E plus to the benzene ring, now I just need to know ways to make E pluses. So I can start with what? I could start with H2SO4 plus HNO3, and if I do that, that protonates the HNO3. It loses water to form NO2 plus. And so now I can add a nitro group to the ring. I can use H2SO4 and sulfuric acid and sulfur trioxide. And what happens there? The H2SO4 takes an H plus and protonates the SO3. So now I form HSO3 plus, and guess what that does? Substitutes for a hydrogen in the ring. I'm going to do a halogen. Take my halogen and react it with either aluminum or iron. The aluminum or iron 3 salt of that molecule. And what happens here is that the pair of electrons from one of the halogen atoms attaches to the metal, and I end up forming a Br or Cl plus and like an AlCl4 or an FeCl4 minus. So the iron pulls the bromine or chlorine apart. And now that X plus, that Br plus, that Cl plus can now do what? Add to the ring. Were there any other ones?
But we have to know the mechanisms of the products that form.
No, you don't need to know these mechanisms to form the E plus. But I just wrote the mechanism of how the E plus adds to the benzene ring. So that would be helpful. Because it doesn't matter what the E plus is. Any E plus has the mechanism that's on the top of the page.
So when you do this, do you add the 2 reactants in with the benzene at the same time, or do you put the two reactants together, form the electrophile, and then add it to the...
Normally the benzene is there.
Okay.
Normally, if I wanted to nitrate a benzene ring, I'd take my benzene and I'd add my sulfuric and nitric acid. And then I would add a nitro group to it. And then so what we're going to learn is, these are boring, right? Because electrophile can, okay, I generate my electrophile, I add to the benzene ring, big deal. Well, then it becomes a little bit more complicated, because what if there's already a group on the ring? Because if there's already a group on the ring, where should I add the electrophile? Should I add it 1,2, 1,3, or 1,4? Which is ortho meta para. Or is it just random? It'd be real helpful if it was random, but it's not. There's a pattern, there's a system. And of course, whenever there's a pattern or a system, we have to answer the question, why? So once I have one group on the ring, I've got to figure out, well, where's the next electrophile going to go? And then when I have two groups on the ring, then I've got to figure out, well, where's the next group going to go? So how from those two groups do I figure it out? And we'll get to this because this is called direction. Okay. So ortho para directors and meta directors. Okay. So you don't have to know the mechanism to make the electrophile, but the electrophile will always add to the benzene ring, the way I drew it.
So when you're drawing an arrow of the H moving to the carbocation, where is the arrow going from and pointing to? So it's going from the H to the, are you drawing it to the bond or to the?
I'm actually drawing it to reform the double bond.
Oh, okay.
So that last step is the equivalent of an E1 reaction,
Okay.
where I lose the H plus to reform the double bond.
Okay.
And in this case, it's going to have to occur to reform the aromatic ring. So there were a couple more in here. Any way I can generate a carbocation, that carbocation is going to react with the benzene ring. And we know lots of ways to generate carbocations. There is There's a Friedel-Crafts mechanism where you add the aluminum trichloride or iron trichloride to a alkyl halide. But any way I can make carbocation, it's going to add the benzene ring, which means benzene, toluene, all these aromatic solvents, you don't do SN1 reactions in them. Because if you did, you would end up with your carbocation adding to the benzene ring. So aromatic solvents and SN1 reactions, not a good choice, unless you want to do that.
Two questions from the quiz for this. Number one, can benzoic carbon undergo SN1? So, like in the example, you had a benzoic HBr attached to the benzoic, and then you added H2O.
What do you think? No reaction? Well, let's lose the bromine. Do I form a stable carbocation? Well, that's a stable carbocation because it's a secondary carbocation. Now, if I erased all this stuff, or some of it, what do I have? What kind of carbocation do I have now? Secondary allylic. So can it form a resonance structure? Yes. I mean, if you're sitting there going, I don't know, can it form a chemical? You missed the last week, at least. Because that's what we've been doing. Which means whoever wrote this book must be a genius. Because they said, oh, well, let's start with allylic systems, and then let's move into benzene systems because they're the same. Right? And every organic book except like one that nobody buys has this same flow. Because once you know how to handle allylic systems, you now know how to handle benzylic systems. Now, you might make the argument, well, if I draw all the resonance structures for this, some of them aren't going to be aromatic. Okay. They're not the most stable. But remember, a resonance structure is a sum of all of its hybrids. So the fact that I can draw 3 more resonance structures of that means that it's going to be more stable than if it was just a run-of-the-mill secondary. Actually, more stable than if it was a run-of-the-mill allylic. So can I form a secondary benzylic? Yes, and I will. Because a benzylic carbocation is pretty stable. In that problem, there's another here's the question. And I could do it from either end. So, will that rearrange? If I have that benzylic carbocation, will it undergo a hydride shift to form the tertiary carbocation? I hear 2 yeses.
It can, but maybe not 100%.
I'll buy that. How do we know if it will or not? Based on they're both intermediates, right? So if I did a hydride shift, the reason that I'm going to do that hydride shift, what's the rule about hydride shifts? You have to form the more stable intermediate or carbocation once you did the shift. So once I shift that hydrogen, does that mean a tertiary carbocation is more stable than a benzylic one?
No.
I don't know. That's the question. That's the question. Which is more stable, tertiary or benzylic? Okay, you can make the argument that the benzylic will be more stable based on resonance. But you can make the argument that the tertiary is more stable because it's tertiary. Exactly, because it's tertiary, right? So the question is which one is more stable? And I could do this, I could basically, if I wanted to really test this, what I should probably do is to get my hands on the bromide in both positions, add water to it, isolate the product, look at it by NMR, and see whether or not the hydrogen shifted in both cases. Right? That's going to ultimately answer my question. And I hope I can buy both of those, because otherwise I've got to sit down and figure out how to synthesize them, synthesize the 2 alcohols. But actually we could handle that. We could put on paper how to synthesize them. Or I can just go to the computer. So, because honestly, I've been a professional chemist longer than I've been a professional educator. So my gut instinct tells me that the benzylic's more stable than the tertiary. But I don't know that for a fact. So we go to the computer and we say, here is a structure. Which one is this? This is the benzylic carbocation, because there's the benzylic, and there it is, sp2 hybridized. And of course, an empty p orbital I can't see because it's empty. Actually, I have a hard time seeing it anyway. So the geometry here is sp2, and the geometry on this carbon is sp3. So then I ask the computer to do a calculation on it and tell me what is its, no, not that. What is its energy? And simple calculation says this is 840 kilojoules. That's its energy. You can think of that as its heat of formation, overall energy, whatever. It's 840 kilojoules per mole. Okay? So then what I do is then I go over here and I say close. Yeah, we'll save the changes. And then I come over here and I say, let's open this up. And now let's do the tertiary carbocation. So here is my, and this is exceptionally slow because I'm logged into my computer up in the lab that has the expensive software that's running this. So can everybody see, here's my tertiary carbocation, sp2, and here's my benzylic in the sp3. So then I come over here to the energy, and the energy is 848. So which one of those two had the lowest energy? The first one, which was the benzylic. So according to these calculations, which they're probably pretty good. If I really wanted to study this, what I'd have to do is put in a whole bunch of different conformations and calculate their energies, because who knows, this is the lowest energy conformation. I might have some rotations that I have to do, and I can do that with this. That's not a problem. I have to do them for both. Maybe the method that I'm using isn't exactly the best. I'm using semi-empirical calculations with the PM3, which is my favorite. But I could use PM6, I could use Mindo, I could use a whole bunch of things. Or I could go into the ab initio world where it starts from scratch and calculate it that way. And I'd have to try all those and make sure they all gave the same answer, which is unlikely because one of them's going to bomb. But this is how I could determine the calculation. Now, 8 kilojoules per mole is the difference. Like, how much is 8 kilojoules per mole? This is something that, as an undergraduate, it's hard to get a handle on. Like, will 8 kilojoules per mole blow up this room? Will it just barely melt an ice cube? It's about 2 kilocalories. It's what? 2 kilocalories, roughly. So is that a lot of energy? And the answer is actually it's not that much. So this is not a slam dunk that the tertiary is is absolutely less stable than the benzylic. But we're going to consider benzylic more stable than tertiary. I'm a professional chemist. I can make that decision. So I just did. Now, one last thing, if I really want to complicate this, and I know everybody just tuned out, but don't tune out. Because we could say, 2.5 kilocalories per mole isn't a lot of energy. But remember that if we're talking about rates, we use something like the Arrhenius equation to determine rates of reaction, right? And the rates of reaction are all done on a logarithmic scale. They're not done on a linear scale. So what that means is what we perceive as a very small amount of energy, once you put it into a logarithmic formula, could change the rate 1,000 times. Right? You raise the temperature of a reaction 10 degrees Celsius, you double its rate. There's no linear relationship there. It's all logarithmic. So I think the benzylic is more stable than the tertiary. And I would have great evidence of that if I put the bromine on the tertiary position and did the reaction, and the nucleophile ended up on the benzylic position 100% of the time. And if I did it, and if I started with the bromine on the benzylic position and I got 0 tertiary position, I'd be pretty convinced that it's there, that tertiary is more, or benzylic's more stable. But I'm thinking of having somebody do that probably over the summer just to see if that really is the case, because that would make a great case study. Because in order to figure out the structure, we have to know NMR, right? Because then I just give you the 2 NMRs of the products, and you'd have to figure out which is which. And then we'd have to figure out how to make these using like Grignard reactions. And that case could take like a week of class time to get all those pieces together. Okay. All right, if there's anything else, send me an email. I will release. Oh, sadly, I didn't bring any practice problems, so you're good for Friday.
I'm going to cry.